All right, good afternoon, good morning, good evening, good night, depending on when you're watching the video. So in this video, I will work through exercise 6 of lecture set 6, which is on slide 27. So this is somewhat of a cumulative exercise. It utilizes a lot of the concepts from lecture set 6, including when to apply central limit theorem, and that's sort of baked into the questions, if you will. Right, so first off, it says there's evidence that the mean age people are diagnosed with early onset dementia is 55 years. So for clarity here, the mean age of diagnosis, which is measured in years, this is our variable of interest. Okay, so we're measuring mean age of diagnosis. So that's the thing that we're measuring. And then, it's a great sentence. In part A, it says, for samples of size 50, okay, for samples of size 50, the standard deviation of the sampling distribution is 0.961. So this thing is actually sigma x bar is 0.961. Okay, so we're given sigma x bar, the standard deviation of the sample mean directly. What is the population standard deviation for people diagnosed with early onset dementia? So what we want here is sigma, all right? So we know that sigma x bar is sigma divided by the square root of n. So a little bit of rearrangement shows that sigma is equal to sigma x bar times the square root of n. So this is 0.961 times the square root of 50, which is 6.795. All right. Okay. In part B, it says, for a random sample of size 50, what is the probability that the mean age, very important. Okay, so it says mean age. We're asking about the mean of all ages. Okay, so for samples of size 50, what is the probability that X bar at diagnosis is less than 52 years? So what we're being asked for directly here is what is the probability that X bar is less than 52? This is what we want to find. And we can say, since n is greater than 30, X bar, or sorry, the sampling distribution of X bar is approximately normal. Okay. So this is important, and this is only true, and keep in mind, when I say only true, when we go back and we read the description of the problem, the only thing we're given is variable and mean age. We're not told anything about the distribution. Hopefully, given what we're measuring, this is a very left-skewed distribution. We'd like that age at diagnosis to be later, I would imagine. And because our sample size is greater than 50, this means that since n is greater than 30, the sampling distribution of X bar is approximately normal. So this is central limit theorem, right? Taking over is approximately normal, and then I should write by central limit theorem. Okay, so here is my sampling distribution of X bar. So this is centered at 55. And what I want, or rather what we want, is this area here. So this is 52. And we're looking for this area here. So this is a this is a Z-score problem. This relates back to what we studied in lecture set 6. So we know we have to standardize first. So Z is equal to X minus mu over sigma. Okay. Now, we are going to let X be equal to X bar here, because we are asking a probability question about the mean age, about the average age, or about the sample mean. So we want to standardize X bar and turn X bar, which is approximately normal with mean 55 and standard deviation 6.795, into a Z-score. So we want to turn X bar into a standard normal. So if we let X equal X bar, then Z is now X bar minus its mean divided by its standard deviation. Okay, and we can simplify this. Okay. So Z is X bar, mu X bar is mu, sigma X bar is sigma over the square root of n. So this is now 52 minus 55 divided by 6.795 over the square root of 50, which is going to be -3 over 0.961 roughly, which is -3.12. Okay, so now we have our Z-score, and that means the probability that X bar is less than 52 is equal to the probability that Z is less than -3.12. So we go to our standard normal table now. So we have -3.102, which is 0.009. Sorry, 0.009. And that's our probability. So now we can say, if we had to interpret the probability that the mean age at diagnosis is less than 52 years is 0.09% for samples of size 50. Part C. Okay. In part C, obtain the probability the sampling error made in estimating the mean age at diagnosis is within 2 years for samples of size 50. Okay, so again, we're working with a sample of size 50, so we can assume that X bar is approximately normal. What are we trying to answer here? We want the following: mu minus 2 is less than X bar is less than mu plus 2. So there's a few different ways that we can approach this. We can do a little bit of simplification right off the start. We know that mu is 55. So this is going to be 55 minus 2 is less than X bar is less than 55 plus 2, right? So this is going to be the probability that 53 is less than X bar is less than 57. Right, so we can visualize this thing. We can draw a standard normal curve here. Center this at 0. Or sorry, this is going to be centered at 55. Sorry. This is a normal curve, not a standard normal curve. Here's 53. On the same side, should be about symmetric. Here's 57. And we want this area here. Right. Okay, so this problem, we just have to standardize our two limits now. So we can say Z1 is X bar minus mu over sigma divided by the square root of n. So this is 53 minus 55 over 6.795 divided by the square root of 50, which is negative 2.08. And then Z2 is X bar minus mu divided by sigma over the square root of n. This is 57 minus 55 over 6.795 divided by the square root of 50, which is 2.08. So this thing becomes the probability negative 2.08 is less than Z is less than 2.08. So this is the probability Z less than 2.08 minus the probability Z is less than negative 2.08. All right, if we go to our standard normal table, we look up 2.08, which is 0.9812. And then we look at negative 2.08, which is 0.0188. Then we end up with 0.9624. Okay, so then we can say something like the probability the sampling error made in estimating the mean age of diagnosis is within 2 years or is 96.24%. So the probability that the sampling error made in estimating mu, or the made in estimating the mean age at diagnosis for samples of size 50 is within 2 years is 96.24%. All right. Okay, in part C, or sorry, part D, we're doing the same thing, but we are just increasing sample size to 100. All right, so we should see a decrease in the sampling error here. Okay, so we're doing the same thing, but we're increasing to samples of size 100. -2. Okay. Strange. All right, so okay, so we want probability mu minus 2 is less than X bar is less than mu plus 2 again. So this is going to be the probability 55 minus 2 is less than X bar is less than 55 plus 2. Okay, so this is, again, the probability 53 is less than X bar is less than 57. So the illustration is going to be exactly the same. The only difference here is that when we standardize, so for example, Z1 is X bar minus mu over sigma divided by the square root of n. This is going to be 53 minus 55 over 6.795. divided by the square root of 100 now. And this is negative 2.94. Okay. And then Z2, which is going to be 57 minus 55 over 6.795 divided by the square root of 100. That's going to be positive 2.94. Okay, so this thing becomes the probability Z is less than 2.94, or sorry, the probability negative 2.94 is less than Z is less than positive 2.94, which is the probability Z less than 2.94 minus the probability Z is less than negative 2.94. Okay, so we go back to the table. We have negative 2.904, which is 0.0016. And then we go to the positive side, and we have positive 2.94, which is 0.9984. Okay, and that gives us 0.9968. So essentially what this is saying is that it's even more likely for an increased sample size that the error is within 2 units, okay, which makes sense. It's basically saying that because the sample size is increased, we have a higher probability of containing the error in estimating the population mean to within 2 units of that mean, or to within 2 years. All right. So if we wanted to, the interpretation here would be the same as in part C, except where it says samples of size 50, you would just have samples of size 100. Okay, in part E, it says, suppose we collected a random sample of size 20. What assumption would we have to make to find the probability that the sampling error made in estimating the mean age at diagnosis is within 2 years? So basically what this question is asking is, if I only had a sample of size 20 now, given what I know, how can I still perform the calculations in part C and part D? What would I have to assume? In order to compute the probability that the sampling error is within 2 years of the population mean age at diagnosis, we would have to assume that age at diagnosis, which is the variable, is normally distributed. Okay. So for a sample of size 20, because we don't know what distribution the variable follows, the only way that we can perform the calculations that we had in part C and part D is to assume that the variable is normal. Because if the variable is normal, we can assume the sampling distribution of X bar is normal, regardless of what the sample size is. Okay, otherwise, we cannot perform the calculations in C and D because we don't know the distribution of X bar. All right. Okay, so as always, if you have any other questions, please let me know.